Hi everyone, I'm Minghao Chen. I'm currently a second-year DPhil student at the View Geometry Group at the University of Oxford. I'm glad to present our work, Training Free Layout Control with Cross-Attention Guidance. This work is done by me, Dr. Laina, and Professor Andrea Vedaldi. So in summary, in this paper, we present a method for controlling the layout of the images generated by large pre-trained text-to-image models by guiding the cross-attention patterns produced by the models in a spatial-directed manner. One big advantage of our method is that it requires no further training or fine-tuning. As shown in the bottom figure, with additional input like bounding box, our method can control the layout of the generated images, such as the positions of the horse or the pandas. The motivation behind our method is simple. First, despite the success of text-to-image generation, however, many practical applications of image generation, particularly in a professional context, require a high level of control that current methods lack. Second, current state-of-the-art text-to-image generators often misinterpret simple layout instructions specified via text. For example, the strong text-to-image generator, the Stable Diffusion, cannot understand simple layout text instructions such as a dog to the left of a cat, a cap above a clock, or a track below a horse. Therefore, we ask if we can find a way to control the layout of the images generated by the pre-trained image generators. Actually, this is a task called layout-to-image generation. There are some works trying to solve this problem, and they can be mainly classified into two classes. The first class is called closed-set vocabulary model, which means the model is trained on dataset with finite classes, such as MS COCO. The other one is called open-set vocabulary model. They do not limit the labels of the input bounding boxes. Our method tries to solve the open-set problem. Although there are some works such as Collision and Recall focus on this setting, they usually require training or fine-tuning an open vocabulary image generator, while we try to solve it without further training and fine-tuning. Our method is based on the latent diffusion model called Stable Diffusion. Stable Diffusion can control the output of the image generation given different conditions, such as tags, semantic maps, depth maps, with the mechanism called cross-attention. Here we mainly focus on text as our condition. In fact, cross-attention is the only place where the image generator receives text information, different from self-attention, where the query, key, and values are all from the input, that's the images. In cross-attention, the query is from the images, and the key and values are linear transformation of the text embedding, and the output is a weighted sum of the value. Inspired by previous work, we found that the cross-attention maps reveal strong spatial information of the generated images. For example, the cross-attention map of the word dog shows the basic layout of the dog. Therefore, we have the idea to control the layout of the generated images by manipulating the cross-attention map. Now we propose our first approach, forward guidance. Given text prompts such as a dog is playing on the grass, we take out the cross-attention map of the word dog and manually make it focus more on a given bounding box area by injecting a Gaussian blob to its cross-attention map. In addition, we find that the spatial tokens, that's the start of text token and the end of text token, contain significant amount of spatial information about the layout. They seem to be complementary, where the start of text token focuses on the background and the end of text tokens show the foreground information. Therefore, we consider also applying forward guidance on the spatial tokens, that's the start of text token and the end of text token, to strengthen the layout control effect. The second approach is called backward guidance. Here we also take out the cross-attention map of the word dog. But in contrast to the forward guidance, we do not hardly change the cross-attention map. Instead, we design an energy function and compute the loss between the cross-attention map and the given bounding box. After that, we backpropagate the loss to update the network latent. Now let's turn to the experiment section. We quantitatively evaluate our methods mainly on three datasets. the Flickr 30K entities, the Coco 2014, and the Visor benchmark. We compare the proposed forward guidance, backward guidance, and find that the backward guidance achieved better performance. We further compared our method with previous and concurrent methods. Then we provide some qualitative experiments, including the synthetic image layout control and the real image layout control. At last, we provide some ablation studies. As shown in the first row of the figure, using only forward guidance sometimes cannot change the layout significantly. If we are also applying the forward guidance on the start of text token and the end of text token, we can achieve better control. However, it is still worse than the backward guidance. In the bottom table, we give a quantitatively comparison between backward guidance and forward guidance on the Visor benchmark. We can see that applying forward guidance on spatial token does help the layout control, while backward guidance is still better. Besides, we can further boost the performance by selecting the initial node using the loss function defined in our backward guidance, which is shown in the last row of the table. We provide quantitatively comparison with other methods on the three different datasets. As shown in the table, our method achieves superior performance compared to other previous and concurrent methods, and it is also capable to increase the performance of other trained layout-to-image models, such as Ablation. Here we provide some qualitative comparison with other methods. As shown in the figure, methods without layout control generally struggle to follow the spatial instructions in the text. Even methods with layout control can sometimes generate wrong layout. Instead, as shown in the last row, our method can generate a right layout. Even the two objects, the ball and the snowboard, in the text are usually not seen together. Here are some quantitative examples of synthetic image layout control. Given text prompt and some bounding boxes, our method can control the position, size of single and multiple objects. We further demonstrate the ability of our method by extending it to real image layout control. With the help of text inversion and dream boost, we can first customize the diffusion model to this specific corgi, and then apply our method to control the layout of the customized model. At last, we showed some ablation studies of our method. First, we show that there is a trade-off between realism and the control strength. By increasing the loss scale in the backward guidance, we achieve better control, but we gradually lose the realism of the photo. We also give an in-depth investigation about the optimal layers for manipulating the cross-tension map. As shown in the table, we find that the combination of the mid block and the first block in the upsampling branch of the unit get the best performance. In the end, we give some potential research directions. First, we might do some controllable 3D generations. We can actually lift the 2D layout control method to 3D by projecting input 3D boxes to 2D. And also, there are something we can do in geometry control. Current method cannot control the geometry direction of the generated object, and it might be possible to do it with some manipulation in the text space. And second, one might control the specific shape of the object by defining a different energy function. That's all. Thanks for listening.